So I'm just gonna make one up on the fly for the basicity part of this question. And then go ahead.
Can we do part B?
Yeah, I'm gonna do part B too, but somebody asked for a basicity. I'm just gonna do a quick basicity question. So this is gonna be basicity.
I just have a quick question before you get started. On the one we did before that, you said that can you just scroll up a little? You said that you said D is more acidic than E?
Less.
Less?
So
Why is
D
it less?
so D is no, D is more. D is more acidic. That's why it's 5 than E.
What's the significance of the F being connected? Is that the case?
This is an inductive effect from an electron withdrawing group. This is an electron withdrawing group. It helps stabilize the negative charge.
Okay, thank you.
Okay. Right. So basicity, real quick. Just to illustrate all points, I'm having. Let's do a couple. Let's do it. Here, let's do this. Let's do this one. Down. My group. So my group. So and okay. In terms of basicity, go. What do you guys think? What have you learned so far? We're gonna pronate this, or are you guys good just working backwards? What would be your most acidic?
I have a question about basicity.
Right.
When you're finding it, is it like finding acidity, but it's just backwards?
Yes.
Okay.
Yes. So if I'm asking you right now, what would be most acidic?
It would be the one. Would it be the one at the top right?
Yes. Why?
Due to the hydrogen bond.
No, it's not due to the hydrogen bond. Anybody else? Why would
the negative
A
is
be
on the most
acidic?
electronegative?
Okay, no, because they're all connected to oxygen. So here, they're all connected to oxygen except for E and except for C.
Because
so
the
right.
negative
A, go ahead.
Because the negative charge is not connected to the oxygen.
No, I'm talking about most acidic right now.
Oh, okay.
What would be most acidic? Anybody? Think about what we just talked about, the inductive effect, right? So if we have two heteroatoms, two halogens that are extremely electron withdrawing, and they're a couple carbons away from the negative charge, do you see a pattern? This one has two electron withdrawing groups, right? Compared to this one, which has none. This one has none. This one only has one. This one only has one. And this one's not even an oxygen, nor is E. So based on not only the A in cardial or aerial rules, also the I, the distance from the inductive effect. The distance from the inductive effect is essentially two carbons away, but it's double. It have two groups, 1 and 2. So this would be most acidic, meaning if something is most acidic, it's less basic, correct?
Yeah.
Yes.
Okay, so this would be 1 in terms of basicity. I'm gonna do basicity. So this would be least basic, right?
Yes, but is this least basic? Explain why this is least basic again.
It's least basic because it would be the most acidic compound. This is the conjugate base. This is the conjugate base of an acid.
Okay.
So once we deprotonated that, this was originally an acid, and then we got it to be deprotonated. That's why there's a negative charge here. The negative charge has resonance, and it also has electron density being pulled away from it from both electron withdrawing groups, from chlorine and fluorine. So now let's look at the other groups, see if any of those look similar, and see if any of those have an inductive effect as well. Out of B, C, D, E, and F, which one also has an inductive effect?
B and F.
Would be B as well.
Okay, so which one would be less basic? B or F?
B. B.
B, you're right, because it's only one carbon away from the carbonyl, from the carboxylic acid. So this would be number 2. And with that logic, we can also say this would be 3. Okay, now compare C, D, and E. What's the difference here? So they don't have inductive effects going on, okay? But we can still think of our Orgo rules. Which one is connected to the more electronegative atom? Is it C or is it D? What's more electronegative? D, correct.
D.
So D would be 4 because it would be much more acidic, so technically less basic than an amide. And now we have that amide, and we're comparing the amide to an acetylaldehyde or acetylide ion, I believe. Acetylide. That's what this is. This is acetylide. Can anybody tell me what? In this case, this is a perfect example of why sometimes the Orgo rules are taken with a grain of salt. Because here we have A taking the priority, electronegative atom, right? But here, this is O taking priority. O would be orbital. So can anybody tell me the orbital? This looks like this. So it's a carbon, it's a terminal carbon with 3 hydrogens, right? An internal carbon that is triple bonded to a carbon and the negative charge. Okay. Can anybody tell me what is the hybridization state of that carbon?
SP.
SP, correct. And what did you guys learn about SP?
It's the most acidic.
Why is it most acidic?
Least distance from the nucleus.
Correct. So having that in mind, what do you think takes more priority? The electronegative atom or the orbital? What would be better stabilized?
Orbital.
Orbital, correct. And if you can always double check, you can go to your pKa table and look up the pKa for an amide and look up the pKa for a acetylide ion. And you'll find that acetylide ions can be anywhere from like 25 to like 50. It's something huge. But this one's going to be slightly lower. Okay. So your answer would be 5 and 6 as your acetylide ion being the most basic. And you'll learn about this in chapter 9 as well, why the acetylide ion is such a good base. It's a good deprotonator. So going back to your acidity question, okay, rank the following in acidity. And here we're also going to think of the C in cardio. Cardio. Is there a charge on here?
Yeah, on the O.
Okay, would that make it the most or least acidic? We're talking about acidity. We're talking about acidity, not basicity.
The least.
No, it'd make it the least because this is a negative charge. Think about what a Lewis acid and a Lewis base is. It talks about Lewis bases being electron donors, right? or electron acceptor. So the difference between an electron donor and an electron acceptor. Here it's acting as Lewis base, not a Lewis acid. Correct?
Got it.
Because this would donate its lone pair to pick up a hydrogen, to pick up a proton. So this would be number 1, right? Now let's compare the other ones. We already saw the most acidic here. Which one would be the most acidic? We're comparing this hydrogen to be specific. So they don't do a good job of labeling the hydrogens, but we're comparing this hydrogen, we're comparing this hydrogen, we're comparing the hydrogen that's here. So if I was to erase this lone pair hydrogen here or hydrogen here, here we're comparing this hydrogen, and here we're comparing this hydrogen.
Would it be E?
No, C is most acidic. Remember we did this example about like if this was a negative charge, it could essentially donate either way.
I said E, not C.
Yeah, E is not the most acidic. The question was which one would be the most acidic out of these 6? C would be most acidic. Is that making sense? Does that make sense to everybody?
Yeah,
Why that is? Okay.
yeah, the orbital.
No, it's C. This one's C. This one's C. It's the
Oh,
resonance.
okay. I was like, what am I
Resonance,
looking at?
right?
Yeah, okay. All right, now all we have to do is compare the other ones. So I guess we can compare D and let's see which one first. Let's compare, because here we're talking about orbitals, right? This would be sp orbitals. Here we're looking at which one has more resonance and electronegative atom. All right, so if we compare, let's compare B and E later. So B, this is E. Let's compare those later. But let's compare C and F. Which one's more acidic?
How about B?
B?
Sorry, E.
No, we're comparing C and F. Sorry.
Is it C?
Does anybody agree? Anybody else? Does anybody know? So if you don't, does anybody have an idea why this is? Why it's more or less acidic?
What exactly are we comparing? Is it C and E or what?
Yeah,
and
are
F.
no, C and F. We're comparing C and F.
Oh, okay.
Is it because of orbital?
Yeah, so this is what you have to look at. Does this is comparing atom and this is comparing orbital, right? So in this case, this is electronegative atom. The problem is that it has very poor resonance. It has no resonance at all. This one technically could have resonance between both carbons. But this one would be a little bit more stabilized because of the orbital being closer to the nucleus, right? So technically, this would be a little bit more stable. I mean, you can double check the pKa's. I would have to, let me just double check to see, because with these questions, it's a little bit tricky. You have to look at your pKa table and then, come back to your RO. I don't know what pKa table the book gives you. I'm just looking this up online. The pKa for turf butoxide should be around 17. And for the citalide should be no, okay, so your atom takes over. This would be 23. So the pKa is slightly higher. You can see how the difference is very small. Technically, we got this backwards. This one would be more acidic. And this is based on your pKa too. Here, atoms priority over orbital. But you saw how in the last example, it was backwards. Atom didn't take the most priority. It was orbital that took most priority. So that's why you always have to look at your pKa table. In this case, this one's a little bit more acidic. So you have 1, 2, yeah. This is 1, this is 2, this would be 3, and now we just have to compare 5 and 6, which would be B and E. Which would be more acidic? Is it B or is it? Everybody, theory.
E would be more acidic.
Yes, thank you. So this would be 5. Okay. Not too bad. Let's look at let's see. Oh, okay. Let's see. Okay. There's a question from the chapter that you should figure out. Okay. These are good. Okay, let's just quickly do these. Which one is the more acidic hydrogen in each one of these cases? And tell me why. Somebody answer for A.
It would be the second one
Why?
because we're going down the periodic table, so sulfur is bigger than oxygen.
You could look at it, in terms of size, but the concept is polarizability. You can handle that negative charge because of the electron density. The electron cloud of sulfur is bigger than oxygen. Okay, so whether you have that or have a different, another, I'm trying to look at the periodic table. If you had, let's say you had, instead of sulfur, you had, I don't know, Se. We compare SEH, and it's the same structure. SEH would be more acidic than SH. Okay, so the trend is yes, going down, but it's because going down makes things more polar. Okay. How about B?
The one on the
What's more
left due to resonance.
Resonance. Yes, resonance is key. Okay. What about C?
Left.
Left.
Left. Because
Induction.
Induction.
induction. I for induction. Okay. What about D?
The one on the left.
Left.
One on the right.
Is this another case of atom versus orbital?
Yes, exactly.
How would you distinguish which one takes
In
priority?
this case, it's a little bit difficult because there is no more resonance because there's a hydrogen here, right? So it makes it a little bit more tricky. But I would say SP takes priority. I could be wrong though. I don't even have the answers to these. But I believe in this case, the negative charge closer to the nucleus would be better. Because carbon and nitrogen don't have that much of an electron negativity difference. Carbon is like 2.55. So for carbon, the electron negativity is like 2.55. And for nitrogen, it's 3.0. I mean, it's maybe significant, but I would always pick SP. Yeah. But if you get a question like this, it won't be so obscure or so arbitrary. We're gonna make it a little bit clearer, like in B, A, or C. we're gonna give you something else. We're gonna do, like for this question, if we were to compare both of these, we'd probably give you like a positive charge here and like resonance or something. You see what I'm saying? Would make it a little bit more obvious. All right. Cool. Yes.
Yeah.
Okay, cool. Let's see. I have a couple more topics. How do you guys feel formal charges? You guys good on formal charges?
Yeah. Confident.
Confident? Okay. Stability of Newton projections, confident?
No.
No.
Yeah,
No.
you do one of them.
Okay. How about if I told you, we're gonna go from naming to nomenclature. So let's see. I want you to draw three ethyl. Let's make this easier. 2, 3 dimethyl. Next. Draw most and least stable forms. Okay, so how do we go about this question? First off, you have to draw the bond line structure. And so, okay, let's draw the bond line structure. We know it's a hexane, so that's 6. 1, 2, 3, 4, 5, 6, 6. Okay, so that's our longest carbon chain. I tell you that on 3, there's an ethyl. Was 1, 2, 3. There's an ethyl. Here. And on 2 and 3, there's a methyl. So here's a methyl. 3 is also a methyl. Okay, easy. And I'm going to tell you to draw it from the C2 to C3 bond. Okay, so C2 would be front, C3 would be back. So front and back. Unless we give you like an eye showing you where it is, you're going to assume that the first number is the one that you're looking at from the front. Okay, so something like that. All right, so if I want to be a little bit cleaner, what I can do is show stereochemistry, which we may or may not give. It just depends. But if you want, you can always decide to draw stereochemistry just to draw those implicit hydrogens that we're not showing. So this is a methyl group. This is also a methyl group. This is a methyl group, and there's nothing in the back. So let's draw our Mercedes-Benz. So here in this case, I'm looking at the Mercedes-Benz almost like as if it was inverted or to the side. What's on my left in the front carbon? So carbon number 2. This is carbon number 2. What's on my left?
Hydrogen.
Hydrogen, correct. What about on my right?
Methyl.
Yes, ma'am. Pointing down.
Carbon.
Carbon. Another methyl group. Okay, beautiful. Now we're going to draw.
Wait, where did you
our
get the
back
other
carbon.
methyl group?
Down here. This is the methyl group.
Isn't that a carbon? Oh, okay.
That's a carbon
that's the
connected to, yeah, it's a carbon connected to 3 hydrogens. We call that methyl.
Okay.
You see that? I'm not drawing all the hydrogens. And I'm not writing methyl either, but you should understand that that's a methyl group. Okay? All right, what about on our back carbon? And here, I'll just make this a little bit more simple. This is the back carbon. This is C3. So this was C2. This is C3. What is pointing to my left?
Methyl.
Yes, ma'am. What's pointing to my right?
Ethyl.
Okay. And what's pointing up?
Is it
Methyl?
propyl?
Propyl. Whoever said propyl is correct. Propyl. Okay. Now, easy. Now I could just put these like this. Does that make sense to everybody? How I got that? Yes?
Yeah.
Yeah.
Okay, cool. Now, I'm telling you to draw the most and least stable. So let's do all the basically conformations that it can form. And all I have to do is just move one of them. So if this was my parent structure, I'm going to leave my parent structure up there, and I'm going to start modifying it. I'll modify this by twisting the back carbon C3 just ever so slightly, either to the left or to the right, clockwise or counterclockwise. In chemistry, we've already figured out the energy that we could that we need to twist this. So be glad we're not making you do any math, because there's a question in your book that says, what's the energy to twist these? But since we're not asking, we're just going to ask you to twist them to their most and least stable conformations. So if I did the first one like this, let's see. So I did the first one. Oops. I did the first one with methyl. That would be methyl here, and this would be hydrogen here. Is that more or less stable?
Less.
Would this not be the most unstable? What kind of conformation is this?
Eclipse.
Eclipse, right? And so this would be least stable,
I have a question.
highest energy. Yes,
Like,
go ahead.
how do we know when we need to do anti-clockwise and clockwise?
It doesn't matter. I mean, like, there's a logic to this, but you don't have to worry about dihedral angles. All you have to worry about is, like, is it eclipse, is it gauche, is it anti? And the way you determine what is most stable is by looking at the groups. Here we have a methyl-ethyl interaction and a methyl-propyl interaction, but I just could have easily done something else. So let's say, again, I'm copying this, and I'm going to do a more or less stable conformer. So let's say instead of doing it methyl-propyl, methyl-ethyl, now I just keep moving things around. Now I have, if I kept turning this anti or counterclockwise, I would end up with something like this. I have methyl here, but now I have a hydrogen ethyl interaction and a methyl and propyl interaction and a methyl interaction. If you compare these two, this one would be a little bit more stable than what we drew originally. So if this was A and this was B, B would be a little bit more stable, because now it's a hydrogen ethyl interaction instead of a methyl ethyl interaction. I understand that there's still a methyl methyl interaction, but that's less steric. There's less steric interactions with methyl than there is with methyl and ethyl. Does this make sense to everybody?
Yeah.
Yes.
Okay, cool. And now let's see what I could do to make this even more stable. So to make this even more stable, how about we copy our parent structure one more time. I'll put this over here. Now, oops. Now let's see how I can make this more stable. So let's say I now switch these positions up one more time, and now I'm twisting it clockwise. Imagine if I was twisting this clockwise. I would now have hydrogen here, I would have metal here, and then I would have the other metal being here. Since now this metal is now not, it's less closer in angle to the propyl and the ethyl. Now this metal is closer to a methyl and a propyl. Hydrogen has now taken its place. So in this sense, this is a little bit more stable than the parent. And this would be the anti. Okay, so this would be most stable.
I'm sorry, but why is it more stable than the parent?
Because if you look at the parent, so if we compare these two structures, and let me put them side by side. Erase this. I'm going to put this side by side. Side by side. This. Okay, so if we look, where is that methyl group on C3? It's in between the methyl on C2's propyl and the methyl on C2's ethyl. So look here. This methyl group is in between propyl and ethyl. Even though it's like 60 degrees from either side, there's going to be more steric interactions if we're comparing that to hydrogen, because hydrogen has a smaller orbital, correct? It has just one s orbital. So whether it's equal distance from ethyl and propyl, it's still going to be more stable than having a methyl there. And now that methyl has moved 60 degrees to be in between propyl and methyl. If you compare steric interactions between this methyl and the propyl and ethyl interactions, it's going to be less because this methyl is smaller than ethyl. I could have changed this up. I could have put this as a bigger group. I could have made this into a like isopropyl group to make it more obvious. And then you would have like a methyl isopropyl propyl interaction versus a methyl propyl methyl interaction. Does the logic make sense here? Why the one on the left would be more stable?
Yeah.
Yes? Okay. So this one would be most stable. And if this was a number, let's call it B. B would be most stable. A would be least stable. A would be least stable. B would be second least stable. And if we call the parent structure C, this would be second most stable. So if I was to rank these, or if I was just to get the least and most stable, you know it would be A, B. But if I was to rank these, I would make it such that it would be A is less stable than B, which is less stable than C, which is less stable than B. Okay? Yes? You feeling good?
I have a quick
No.
question.
Go ahead.
Are we going to be tested on the Gauss conformations or no?
Not really. It's either gonna be, I mean, like Gauss and staggered. It's like all these things are just names for conformers. The important one is eclipsed and anti. But there's different like forms of them. So like, don't worry about it. Just worry about what's most and least stable and how you can differentiate between ranking the stability of them.
Okay,
which
thank
is
you.
directly based on sterics. Just look at the sterics of it. And
Okay.
for anybody that's still wondering what sterics are, it's the interactions between like big groups, big substituents, like that isopropyl and propyl group. Okay. Yeah. All right. Let me see what else that's going to be on the exam that you guys need to know. You guys are okay with boiling point? You know how to do boiling point? Should I go over boiling point?
Like one example.
Okay, I'll give you one example of boiling point real quick. Let's see. Obvious. Let's see. Okay, boiling point. Is there another boiling point question? Oh yeah, perfect. This one works perfect. Okay, boiling point. Talk to me. What's gonna have the lowest boiling point?
B.
B, correct. Why? Lowest molecular weight, right? Has 1, 2, 3, 4 carbons. Cool. What about the other ones? How many carbons does this have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5, 6, 7. So if we're comparing A and C, which one's going to be lower?
A.
Thank you. And then C. And then this would be F would be 4. How about if we compare C and
E.
E? E would be lower. Why?
More branch.
Because more branch.
More branching, correct. So E would be 5 and C would be 6. Okay, good stuff. Good stuff. I did this question yesterday, but what's the hybridization state here?
SP2.
So why do you think it's sp2?
I see 3 regions of electron density.
Right. Unless we give you something, you are right, sp2. Unless we give you something like this, which makes it a little bit more obvious. How about now? Is this sp2? Let me draw it like this. Or to make it even more obvious.
SP3.
Okay. How about now?
Still SP3.
Is it
No.
SP2?
SP2.
SP2 because it can delocalize.
Exactly. Okay. So just look out for resonance with these questions. Okay. That's I can't stress that enough. Look out for resonance. All right. We did. Okay. Do I have to go over naming, or will you guys understand naming?
Are you talking about like when they ask what is the IUPA?
Yeah.
Yeah,
International Unión de Educación.
I guess like
Something.
on
Yeah.
where to start counting.
Okay. How about let's do an example. Here, let me see if they have a question.
In that question, what does it mean by geometry?
Geometry, whether it's trigonal planar or trigonal bipyramidal or whatever. I have to figure it out.
Okay, thank you.
So if I was to name, I don't know if he taught you how to name complex substituents properly, or just at all. Did he tell you that he was going to do a complex substituent question? Yes, no, maybe.
Could you repeat what you just said? I didn't really hear you.
Did he tell you that he's going to give you a complex substituent question? Because there's a complex substituent.
He mentioned it.
Here. I mean, this is a nice problem, so that it can be considered a little bit different. But if I was to name this, maybe this one is going to be a little bit tricky because this gives 3 complex substituents over here. Let's see if I can. Okay, how about actually just to not include complex substituents, we're going to change this question slightly and take away this, take away this, and take away this. Okay, so view it like that without making things substituents. We'll consider this as alphabetically as C because it's a cyclopropyl group. So how am I numbered? Where am I numbered? Left to right, right to left. Where do you think is the longest carbon chain? Well, let's look at it. There's 1, 2, 3, 4, 5, 6, 7, 8. Is that longer? Or is it 6, 7, 8? You know, whether I go 9, 10 or 9, 10, it's the same.
The 10s are longer.
Yeah, 10s are longer. So now, what are we going to look at? We're going to look at this group.
Substituents.
Yeah. We're going to look at this group. We're going to look at this group. We're going to look at these 2 groups. And we're going to look at this group and this group. So, first one in blue, that is a 3 ethyl, right? 5 is what? It's a 5, 1, 2, 3. How many carbons is that? What's the prefix for that carbon?
Propyl.
Propyl. Propyl. How about on 4? It's a 4. What? I just gave you hints.
Cyclopropyl.
Cyclopropyl. And 8 would be 8. What?
Ethyl.
8 ethyl. And 6 would be 6.
6 methyl.
Dimethyl. Dimethyl. Okay. So now if we're putting this together and we know that it's a decane, all we have to do is put these in alphabetical order. So what's going first?
The ethyl.
No, it's C. C would come first. When it comes to cyclos, C comes first. Okay? So before cyclo, propyl, now it's ethyl. So you're right. How many ethyls do you have?
2. So
So there's
diethyl.
2, 8, yeah, 3, 8 diethyl. What else?
And then 6, 6 dimethyl.
Yes. So 6, 6, running out of space. Dimethyl. Anything else?
5 propyl.
Easy, right? Not too bad. We
Sort
good?
of.
Sort of. Sort of. Okay. I want to give you a bicyclo just because I feel like we did a bicyclo, but I gave you an obvious bicyclo. So I'm gonna do one that's a little bit less obvious, because you need to distinguish the other role in naming, which is locant, which only has the lowest locant or number. So how about in a case like this? How would you name this? Which way are we going? Are we going left? Are we going right?
Right.
You're saying going right?
Right to left.
We're starting at the bridgehead carbons, okay? You're saying let's go right, correct? This way? Or do you mean right going this way?
No.
That way?
The top way.
Okay,
You go
does
left.
anybody agree?
And then you go
Going
left.
left this way? Going left this
Yeah.
way?
Yeah.
Okay, that's also wrong. Does anybody have any better ideas? Okay, do you think, first the question should be, do we start at carbon A or carbon B, or bridgehead carbon B?
Carbon B?
Yes,
A.
correct. No, we start at bridgehead carbon B. We start at bridgehead carbon B, okay? And now, okay, now are we going right, left, or up? Think about it. We all of them have exactly 2 carbons. So it doesn't matter which way we go because the longest path doesn't apply in this situation.
What about the
Does everybody see that?
What about the subs?
Yes, it does. It does. So if I was to go right from here, well, guess what? Look at my locus. They're 1, 3, 4, 5, 6 versus being. Check this out. This is the other interesting point. That we had 1, 3, and 6, right? Now count if we were to go up in pink. This is 1, this is 2, 3, 4, 5. Does everybody see that? We're going up instead of going left or right. Okay, so if I was to continue my count, this would be 6, this would be 7, this would be 8. So from here, I want everybody to tell me we have what's here, a 1 methyl, right? What's here? It's a 2 methyl. What's here? It's a 5 ethyl. We already know it's a bicyclo. And the lengths are 2 carbons, 2 carbons, and 2 carbons. So if we add that up, we have 1, 2, 3, 4, 5, 6, 7, 8. 8, and that's an octane. So it would be 5, if we're going in alphabetical order, it would be 5 ethyl, 1, 2 dimethyl, correct, yes, ma'am. And the bicyclo, here, I always run that space. Bicyclo 2, 2, 2 octane. So just so you know, the point is that you can also go up. If up is your longest path, you go up. Even if it's not, in this case, it's not your longest path, but it is the one that gives you the lowest locus, 1, 2, and 5 versus 1, 3, and 6. Good? Yes. Okay. Are we good? You guys want to do another question? Switch a topic?
Can we do another question?
Okay. What topic would you like?
Wait, no, another one of these questions.
Okay, another bicyclo.
Yes.
Okay. Okay. How about if I do this like this? So what about if I do something kind of like shouldn't mix it. How about let's put a methyl here. How about you guys learn alkyl halides? If I put a chloral here, would you guys get that?
He said he's not doing that on the test. He's not covering that.
Okay. I'll put another. Let's put a. Let's put a propyl group on there. Okay. Bridgehead carbons. Where am I going? Left, right, up.
Would you go up in this case?
Let's see. If we went up, it'd be 1, 2, 3, 4. If we decide to go here, it would be 5, 6, 7, 8, 9, 10, 11. So that gives us 2, 7, and 9. But let's say if we decided to go left, let's see what that gives us. Because I don't know either. I'm just making this up. So if I was to go right or left, 6, 7. So we have 2, 7.
You have to go left from the bottom carbon because you have to start on the longer ring.
Yes, also correct. I didn't even think about that logic. I was just trying to entertain the situation. So yeah, there you go. There's your answer. Bridgehead carbon, longest path. I'm over here not remembering. Okay, left side. Are we going this way or are we going this way? And is that Joseph?
Yeah, it's me.
Hey,
You start
buddy.
on the bottom. Hi, how's it going?
Good. So 1, 2,
Yeah.
3. Perfect. Beautiful.
Exactly.
So let's erase these numbers.
Sorry,
What do
can
we
you
have?
please repeat your reasoning one last time?
Because this is 4 carbons. This is 1, 2, 3, 4 carbons. So we take the longest path. Longest path first.
Oh, okay.
Yeah. And in the first case where we did this way, they all had 2 carbons on each side. So there was no longest path. 2, 2, 2. You see what I'm saying? So it didn't matter. In this case, it does. So this one has 4 carbons. So yeah, good job. Thanks for catching my mistake. Now what? Where do we go? So this is the 1, 2, 3, 4, 5. Which way am I now going?
Up.
Does everybody agree? Anybody?
How about go to the left? Go to the right.
Yes, because we still have to follow the longest path. 8, 9. Now this is 10. This is 11.
Could we have started on the top?
These aren't bridgehead carbons.
Oh, okay.
Okay. So
So
Blue
what
one
do we
is
have
bicyclic, we
right?
always start at the bridges, right?
at the bridgehead carbon? So blue is bridgehead. Bridgehead. Carbon.
Can we start on the top blue?
Yes, but then if you went this way, you would have this methyl group at carbon number 1, 2, 3, 4 instead of being at carbon number
Okay.
3.
Okay.
You see what I'm saying?
Yeah, thank you.
You're welcome. So now let's name them. What's that? 3 methyl.
Methyl,
10
propyl,
or that's propyl. 10 propyl. And 9.
ethyl, ethyl.
Okay, so Easy enough. Now all you have to do is put this in order. This would be 9
So,
ethyl. What's
Three.
next?
3 methyl.
3 methyl. 10
Propyl.
tricycle. So this would be 1, 2, 3, 4, 1, 2, 3, and 2. And how many carbons did we say this was?
11.
What is 11? Does anybody remember? So 11 is un decade. So un decade. If it was 12, it'd be do decade. But don't memorize all of these. We'll only ask you up to 10. So decade.
I understand everything, but the only part that I don't get is when you write the bicycle and then you do parentheses 432. Can you just explain that one more time?
Sure. So these 4, 3, 2s represent the paths. These are the paths. And it's the number of carbons in the path. Okay? So when we went this way, you'll notice now doing it in green, there's 1, 2, 3, 4 carbons. On the right side, there's 1, 2, 3 carbons. And on top, there's 1, 2 carbons. You see what I'm saying? I'm writing that down just to signify to everybody reading this chemistry paper that there's 4 carbons in the longest pathway, 3 carbons in the second longest pathway, and 2 carbons in the shortest pathway. So you have to write the number of carbons in each pathway. That's what this parentheses or these brackets symbolize. Are we good? Did that answer your question?
Yes.
All right, so I believe, I mean, this is basically all the topics. You guys know how to draw chair confirmations. Don't forget to like label your chair confirmations, by the way. You always have to label your chair confirmations.
I have a question.
Go ahead.
Can you explain why we have to write 9 ethyl first instead of 3 ethyl methyl?
Because it's going by alphabetical. So E before M.
Oh, okay.
The previous case, the other naming case question that we did. At the bottom. In this case, we used C to be our first alphabetical because it was a cyclohexane or a cycloalkane rather.
Got it.
Yeah.
Thank
Got
you.
it? Cool. So those are the topics. You have residence, you have let's see, important is residence. You'll have a couple residence questions. Chair confirmations, you'll have at least 1 to 2 of those chair confirmation questions. Numbering which proton is more stable. We did one of those questions today. It's basically this, knowing which proton is more stable, or more acidic rather, which proton is most or least acidic. You'll have one of those questions. You'll have a bicycle naming question. Be sure to be able to name bicycles properly. You'll have a formal charge question, at least the 1 to 2 Newman projection questions, boiling point, ranking acidity, basicity, and functional groups. So unless anybody has further questions, I don't have much else for you, unless you just want to pick my brain on how to take this exam or what questions to ask. you guys have a couple more minutes, just let me know. Are you guys good?
I have a question. From the exam that's fall 2021, and it's 1C. We kind of already spoke about it, and then I've asked it asked us to write the geometry and the bond angle for nitrogen.
Yeah. What about
Yeah, you briefly went over it, but can you just go over it again in detail?
Okay, so what are you not understanding with like this kind of question?
I think the geometry.
Okay, so you know that if this was let's say if this was SP, what is this? This technically will be SP3, right? As it's, or no, SP2 actually as it stands. So this is SP2 as it stands. What would what would it look like? It would be three different groups, right? And this would be in a planar situation. So this would be trigonal planar. The angles would be 120, right? In this case, the angles are still like this is still SP2. The angles would actually be a little bit less than 120. Just because this is pushing down, this pi bond is pushing down on both of these hydrogens. So these are going to be a little bit closer. This would be a little bit less than 120. What else? I think there was another question that we did the day before Friday. So just this, like for example, this one. You understand? Oh yeah, I even drew this for you. This is why it's less than 109 because this electron cloud is pushing down on this trigonal parameter structure. I can give you another example of this if you want. So let's see. Okay, yeah, this one's easy. If I gave you something that looked like this, and I told you what is the hybridization state, bond angle, and geometry of this nitrogen atom, what would you say? Whoever asked the question, what would you say? What's the hybridization state?
SP2.
No, it's SP. Because there's only two characters. The triple bond and the lone pair. In fact, both of these are SP. Both of these are SP. What would the geometry of this be? Excuse me?
Would it be linear?
Yes, it would be linear. It would be linear. And so what would the angle between the triple bond of the nitrogen and this lone pair, what would that be?
180?
Yeah, there you go. Easy. So, yeah, not too bad, right? Not too bad. Does anybody have any other questions? Speak now or forever hold your peace.
I don't remember the name of it, but it's when you did the ring flip problem.
Which one?
The ring flip problem with the I think the chair.
Yeah, those are called chair conformations. What's your problem with the chair conformations? What do you?
Just
what do you
the
have
placement of the things when we flip it.
Okay, so let me do this on a quick page. This will be a good practice for everybody. So, real quick, let me draw something. How about if I draw something like this? Let's say I draw this structure. I draw this structure. Okay. Now, draw me the chair conformation. What would the chair conformation of this be? So this is pointing up, right? This is pointing down, correct? And they are technically trans to each other, okay? They're not on the same side, opposite side, right? Okay, now pay attention. I want to draw, remember, I don't know if you've learned or read in the book how to draw these chair conformations. Basically, just do a big V and you connect all the lines such that they are parallel to each other, basically. You have like this outside being parallel to this outside, this top being parallel to this bottom, and this being parallel to this. That's just how to draw them. It doesn't matter. We're not going to take points off if you don't know how to draw a good chair conformation. Honestly, I suck at drawing. But in the first position, I want to tell you, like, look at this as if it was, as if all the positions are alternate. So I'm going to draw this in gray just to show you what the initial structure looks like for any chair conformation. The initial structure starts, you don't have to start like carbon number 1 here. You could have carbon number 1 be here, 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 or here. It doesn't matter, or you keep carbon number 1. All you have to do is be consistent. But by convention, most chemists use this position as carbon number 1. And at carbon number 1, usually this is what's going to happen. You'll have, not usually, most times, you have a hydrogen pointing up. This is going to be axial. Actually, I'm going to draw everything in red is going to be axial. Everything in blue is going to be equatorial. So this is going to be pointing down, equatorial. This is going to be pointing, now axial and equatorial switch. So now this hydrogen is equatorial. This hydrogen is now axial. And you go the same way around. So now you have this red axial. This would be going this way. This is equatorial. Now this would be axial here, equatorial here, axial, axial, equatorial, axial, equatorial. And notice a pattern. So if you notice the pattern, at every point on the edges, here and here, on the top, they're pointing up. And on the bottom, they're pointing, oh wait, I missed this one. Should be the opposite. Axial. So notice all the edges on top are pointing up. Okay, and the opposite is true for equatorials. And in the middle, this point, because V is kind of pointing down, that hydrogen is axial pointing down. The opposite, V pointing up, like this, has the axial position pointing up as well, right here. Okay, so that's just knowing how to draw a proper chair conformation. This structure is just a simple cyclohexane. There are no substituents on it. In this case, I'm giving it 2 substituents, carbon number 1 and at carbon number 2. So carbon number 1 and at carbon number 2, we have 2 substituents. Is it pointing up or is it pointing down? Is the isopropyl group this? Is the isopropyl group pointing up or pointing down?
Up.
Up. Thank you. So what position would it be in?
The axial.
Yes, correct. All right, now what about carbon number 2?
Pointing down.
Yes.
Axial.
This methyl group would be axial, correct?
Yeah.
Okay, perfect. Now let's ring flip. Erase this, and let's ring flip.
Isn't the methyl group supposed to be equatorial?
Now this is pointing down,
Dashed.
so it's axial because it's pointing down. This hydrogen here is signifying that it's pointing up.
Oh, okay.
Okay. So when we're ring flipping it, it's basically the same structure, but it's a reflection. So if you look at this reflection, try doing my best as straight as possible. Ugh. All right, that was good. Okay. Now, ring flip. Carbon 1 is now at this position. Everything moved clockwise. So this would be carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. That's easy. Okay. Carbon number 1 is isopropyl. What position is it in?
Equatorial up.
Yes. Correct. What about the methyl group?
Is equatorial down.
Yes. Good job. Perfect. Good job. And so
I have a question.
notice, go ahead.
For the methyl group, isn't it like a dashed line, so it's supposed to be equatorial?
Excuse me?
For the methyl group, isn't it a dashed line, so it's supposed to be equatorial?
No, dash lines don't mean equatorial. Dash lines mean that things are facing away from you. It means that it's essentially pointing down.
So
This dash line means that it's pointing away from you, so it's pointing down.
how do we know when something's supposed to be axial and equatorial? Like,
You look at the way it's drawn. So, for example, here, this hydrogen on this group would be pointing down. So it would be pointing down like this, hydrogen number 1. Okay, better question. How about at carbon number 4? So at carbon number 4 here, and if I was to change this group to a chloral group, whoever just talked, can you please tell me where the chloral group would be once we ring flip? Wait, that's not carbon number 4. That's carbon number 5. That's carbon number 5.
it would be on the carbon 6?
No, it wouldn't be on carbon 6. It's conserving its position. It's still on carbon number 5. But can you tell me whether it would be equatorial or active?
It would be equatorial.
Okay, so it would be pointing up equatorially, right? It would be pointing this way up, and it would be equatorial, right?
Yeah.
Equatorial, right? So do you get how when the ring flips, whatever is axial becomes equatorial, whatever is equatorial becomes axial?
Thank you.
Okay. Does anybody else have more questions? Anybody? I can't see the chat, so I don't know if anybody's asking questions. Are we good?
Yeah, I think so. Thank you.
Okay. If anybody
Yes,
else
thank
has
you.
more questions, speak now because I have to leave in like 20 minutes. So you have a couple more minutes. No? Is everybody good? Yes? Okay, cool.
Thank you.
You're welcome, everybody. Your
Thank you.
exams tomorrow. Be prepared. Be there early. Be there at 9. And you should be done in like an hour. No problems. Okay?
Thank you.
Do you
Okay,
know
everyone.
how many multiple choice and the short answer?
I mean, I don't know. It's like specifically, like there's a couple of questions that will be multiple choice. There's some that won't be multiple choice. I think Eric is gonna try to make as many as multiple choice as possible, but that it doesn't help you, like knowing if it's gonna be multiple choice or not. It just eliminates, a couple wrong answers. So I'm not sure how many are gonna be multiple choice, but there will be multiple choice. But that's not to say that these questions are easier. It just ends up being that you have to actually figure out the answer. Because the answers are going to be similar. Okay.
Okay, thank you.
You're welcome. All right. If everyone's good, I'm gonna end the meeting. Okay. All right. Take care, guys. Good luck.
Thank
Good luck
you.
on your exam. No problem. Bye.